I'm a philosopher of science. I work on kind of how policymakers use expertise, really. And so I work on this sort of boundary of philosophy of science and decision theory, and thinking about how scientific evidence gets incorporated into policy decision making. So today I'm going to talk to you about climate simulation models and some questions about what kind of evidence they provide and how it gets used by policymakers. So I'll just give you a little bit of information about climate science and climate modeling. I don't know how much you know about those topics. It's going to be fairly high level. And then I'll offer some highlights from literature, interesting thoughts people have had about what kind of evidence we get from these simulations. And I'll close by talking a bit about uncertainty in particular and how it gets handled in climate science. So, climate science introduction, the climate. I assume you all are familiar with this. You can hardly avoid thinking about the climate these days, but the word climate refers to the prevailing weather conditions, so patterns of weather over space and time. And what climate science does is it studies how the Earth's atmosphere, oceans, land surface, ice sheets, and biosphere interact in creating its climate. Now, obviously, its primary focus over the last few decades is climate change. We know anthropogenic emissions of greenhouse gases are warming the Earth. And so climate science is engaged in answering these very practical policy relevant questions. How will the climate change in the future, both in the short term and in the long term? And since we want to do something about that, how will various interventions that we could make on the way we live our lives, on industry, on energy use in particular, how would that affect the course of this change over time? And so as Anna-Ruth hinted at, the kind of orientation of climate science is very much forward-looking and an attempt to make these predictions over hundreds of years, really, which raises some particular challenges for it. Now, it's obviously a very complicated task because the climate system itself is a very complex system. So I named there 5 components that climate scientists think of as making up the climate: the atmosphere, the oceans, the land surface itself, its mountains and crevices and so on, and then ice sheets, glaciers, ice caps, and then plants, the biosphere, and animals also interact with the climate. So that system is hugely complicated. It has all of these interacting pieces. It's changing over time. But of course, it's coupled to another very complex system, us. And we are an enormous influence on the climate because of industrial activity, because of the way we change the very face of the planet through land use, because of migration, both human migration and migrations that we cause amongst other animals, and just the level of population and population concentrations. All of these affect the climate as a whole. And so you can see this diagram here that comes from the recent IPCC report from Working Group 2, which shows kind of 3 systems interacting. The climate itself up at the top interacts with ecosystems, including biodiversity, which interacts with human society. And there are all these arrows going back and forth. I'm not sure if they're not exactly causal arrows. There's some causes here, we've got impacts. And the thought behind this diagram is that we know that these systems interact with one another in a way that causes climate change. We also know that we're trying to do something about it. So you can see from human society leading upwards, there's an arrow that says adapt, maladapt, mitigate. We're attempting to change climate change itself, and this itself will contribute to influences on the ecosystems and may worsen climate change, may better it, and so on. So it's a very complicated exercise because of all of the factors that are involved. So what is climate science trying to do? Well, as a science, it has a portion which is just interested in the classic things that scientists are interested in, just understanding this system. And there's definitely still a trend amongst climate scientists of wanting to preserve a little corner of pure research, just understanding this interesting object. It also has a backward-looking component, trying to understand and explain past events, past climatic changes, ice ages, things of that sort. But it's primarily interested at this point in predicting future climate change. And it's trying to provide us with causal understanding because we want to understand what the kind of key levers are that we can change in order to change climate change. Now, right, so this is just to focus on the complexity. Now, what is it that they're actually studying? What are they trying to predict? These are the sort of variables, like the central objects of study in climate science. So first, I think it's important to just highlight this distinction between weather and climate. So weather's what you get, climate's what you expect. The weather is the stuff that's happening now. It's also constantly changing, and it's famously difficult to predict. It's a highly variable and chaotic system. Climate is a kind of summary of it, and there's this important sense in which climate is a statistical concept. So the variables we're interested in are weather variables, things like air temperature, rainfall, sea temperature, and so on. But climate variables are averages or degrees of variation for these. So the objects of interest to climate scientists are like 30-year averages of temperature, or rainfall for an entire region, like Scandinavia. And that's why you hear about things like the classic variable global mean surface temperature. And when people talk about changes in global mean surface temperature, they're typically talking about a global mean, so it's a mean over the whole planet, and a temporal mean, a 30-year average. So when you talk about like global mean temperature at 2100, it's an average in these two senses. So why is this part of the definition of climate? Well, because the system has so much natural variability, the weather is constantly changing and the interactions are chaotic. These climate states are attempting to capture broader patterns. That's important in a couple of ways. One, climate scientists are trying to minimize the effect of short-term variability. And two, any prediction about a climate state is going to be compatible with really different weather states. So when we say that the climate looks a certain way, that can produce very many different days of weather that are consistent because the climate state is such a big average. And then climate change, given that the system is varying so much, what does it even mean to say that climate changes? Well, it means that something external is forcing the system out of its natural range of variability into some new range of variability. And so those changes could be like the reception of energy from solar radiation, like we might change how reflective the atmosphere is or something like that. And then of course, it's just the classic one, emission of greenhouse gases will change how the atmosphere holds on to heat. Right, so we now have this picture. We have an enormous complicated system. The system itself is highly variable. What we're studying are these broad statistical variables attempting to capture patterns. How does one even go about doing this? Well, the key tool that I'm interested in is models. So what is a model? In a very abstract sense, a model is a representation of a system that we use to study that system. So modeling is a kind of indirect form of inquiry. What you do is you construct a representation of the system. So there's the climate, it's a feature of this planet that we live on. It's a kind of abstract statistical feature, but nevertheless, it's a feature of a concrete physical system. Instead, we construct a model that in some way represents this climate, and then we can manipulate and intervene on the model. And by studying the model, we hope to make inferences about the target system, the real world. So there's an important sense in which this kind of inquiry is indirect. And it's also famously simplified, idealized, and partial. So models never attempt to capture absolutely every feature of the system that they represent. They try to isolate the most important features for the purpose of a specific study. So it requires the scientists to identify a set of purposes, to pick out a set of relationships that they take to be really important, and then to use those to construct a representation which hopefully faithfully captures that set of interactions. And then a whole bunch of work is done in establishing that it was safe to leave out the other stuff, and again, relative to a set of purposes. So I have this little diagram here. We have the real thing we're interested in, that's the hurricane approaching Florida. And what we attempt to do is capture it in a model. The kind of model that I'm going to be interested in is a computer simulation model. So it's ultimately represented by a program on a computer. And it generates this thing called a simulation, which really is just a set of numbers, a kind of complicated set of numbers specifying all the variables, and then a whole set of those at different points in time, which are then used to generate these visualizations so that you get a picture of an evolving weather system or a graph of changes of temperature. Okay, but the thing that you're primarily working on when you do an experiment in climate science is you're intervening on the model to make changes in the model, and then you're examining the different outputs that you get. So at a high level, here's a picture of how I sort of think about the inputs to this. There are some physical processes, the actual interactions between parts of the climate system. So the atmosphere has certain kind of circulation systems we're interested in. There's radiation coming in from the sun. There are the currents in the ocean and so on. We represent those. And in the first step, they're represented in a kind of mathematical description using equations from physics. So fluid dynamics, thermodynamics, and so on. And those are then implemented in a computer model. So a computer program is created which solves the equations iteratively, step by step, and produces these time steps. So at time 1, these are the results, and then given that at time 2, these are the results, and so on. And each of these steps involves this kind of simplification, approximation, idealization. So when moving from the actual physical process to the mathematical representation, you've got to do all the classic stuff that makes science difficult. You collect the data, you represent it in a kind of formal representation using scientific theory and so on. And then you have another step where you have to represent that mathematical apparatus in a computer program, which requires, again, using some approximation techniques and heuristics to get it into a form where it is then capable of producing a simulation that gets you something like this visualization, which shows you first historic and then future temperature changes. This is not a visualization of data, by the way. This is a visualization of a climate model reproducing temperature changes over time. Okay, so it's a complicated process to get to this kind of simulation, which is then the primary object that's used in climate experiments. And I want to just focus on one aspect of the move from the mathematics to the computer simulation, which is that the equations in physics that specify the dynamics of the system, like the fluid dynamics, the movement of the air and the ocean, these are captured using differential equations. And these differential equations specify mathematical functions, which are continuous functions. So time and space in these equations are continuous variables. But computers are discrete. They calculate in discrete steps. And so one important thing that I think is not really intuitive if you haven't encountered this kind of model before is that they have to work out how to discretize these equations. And so one important way of doing that is that they take this sphere of the Earth and they convert it into a three-dimensional grid, as you can see in this picture. So you've got stacked layers of the atmosphere, and at the bottom you've got the land and the ocean, and you create little boxes. And why do you do this? Well, because it allows you in the computer program to solve the equations just at points inside each of these cells. And then you simplify massively by having each grid interact with each grid box interact with the boxes around it, and it exchange its heat and radiation and moisture and so on. And now this makes the whole process possible. It makes it work, but it does mean that you've massively changed the nature of the system from a real system in which everything is connected, and of course the physical interactions are happening at kind of every point, and you've just simplified it massively into this setup where you've just got little points and they interact only on the boundaries. And originally, these grid boxes were very large. They were kind of 200 kilometers on a side. And that meant that there was a lot of loss of detail. So a lot of things were not represented in these models. Now, as the technology improves and computers get better, they can make the boxes smaller and smaller. Okay, so a final bit of setup here. When these models are constructed, there's a kind of preferred path, which is the one I gestured at before, which is that you have a bunch of observations about the climate and you kind of capture the important relations using scientific theory, climate physics, atmospheric chemistry, and so on. And so you get some equations that are meant to represent the relationships. And then you put those into the computer model. So you use some tools from applied mathematics and programming and statistics to get this discretized computer program version that is the computer simulation model. But you can't always do that because sometimes you just don't have this middle step. And so sometimes there just isn't really good theoretical understanding. Or in other cases, you do have that, but it's really difficult to represent it properly, as it were. And so there's also a kind of shortcut step where you attempt to represent some features of the climate just directly in the computer simulation without going through this kind of ideal theory-based representation in the model. And that's what's called a parameterization. So a parameterization is when you turn a process into a parameter. A parameter is a number or a set of numbers. And they can capture anything that you've left out of the model, either stuff you didn't understand or processes that are too small. So they happen only inside those little grid boxes. And the classic example of this is clouds. So clouds are hugely important to the climate. I mean, they're where the rain comes from, but they also reflect sunlight back into space. And at any given time, something like half the Earth is covered in clouds. So it's kind of a bad thing that clouds are not directly represented in the model because their size is too small. So what climate scientists do very cunningly is that they have separate models that work out how the clouds work, and then they kind of put the cloud effects in, from the outside. And that's an example of parameterization. Okay, so that's enough. Now you know a bunch of stuff about climate science. Now let's do some discussions about evidence and what we can get out of them. So first question, what kind of evidence are we getting? So we run these things and we get, I showed you this visualization. We've got temperature changes over time, and this is a kind of forward-looking prediction. So one interesting question is, supposing that this is giving us some kind of evidence about the climate, what kind of evidence is it? So one interesting recent philosophical argument about this is that they provide higher order evidence. So this contrast is between first order and higher order. So first order evidence is evidence regarding some proposition, some claim, or a hypothesis that bears directly on it. So the top picture is meant to be an example of this. The raindrops on my window are first order evidence for the fact that it is raining outside. That evidence bears directly on the hypothesis that it's raining outside. Higher order evidence, by contrast, is evidence about the existence or merits or significance of some other evidence, where the other evidence is first order evidence. So an example here might be the fact that a pathologist tells a patient that a tumor is benign. That's evidence that there exists some first order medical evidence that the tumor is benign. Now, the patient may not know what that is. In fact, they often don't know or they can't understand the significance of the first order evidence. So the pathologist's testimony to them functions as a kind of proxy for the relevant medical evidence. And what Parker has argued in a recent paper is that simulations could only possibly provide higher order evidence. So let's think about first order evidence first. So could simulations give us first order evidence about the climate system that they're modeling? So the clear cases of first order evidence are just observations with a fairly direct connection between the observation and the thing it's evidence for. And sometimes climate scientists and other scientists talk as though simulation results are measurements or observations, So I'm sure you all heard statements like this, COVID models are showing us that infections will rise in June. But in fact, if you recall this diagram, there's a really complex process of kind of mediation between the result of the model and the system that the model is meant to target. The model contains bits of physical theories, approximation procedures, parametrisations, and so on. And for any model result, in fact, scientists have to do a lot of work to establish whether that result should be taken seriously or whether it's an artifact, a kind of accidental result of some of these approximation techniques or simplifications. So there's a lot of mediation in a way that makes it seem quite disanalogous to something like just observing raindrops on the window. And so what Parker offers is this kind of account, that there is some first order evidence out there. And what it is first order evidence about, which is facts about the state of the system at a given time. So in this case, this is like historical and current observational evidence about states of the climate. These things were used to inform the model. They were plugged in as initial conditions for the model that it then used to run and calculate future steps. So those facts about the past and current state of the climate are evidence for a hypothesis about the state of the system at a later time, this future prediction, under certain assumptions, given certain scientific theories like the laws of nature that are in the model, and given that they were successfully implemented in the model. So the thought is that the model results themselves are kind of higher order evidence that this first order evidence gives us support for the hypothesis, where the hypothesis is, whatever the climate model said, like warming at 2100 will be X degrees. And so the idea is to use this kind of complicated mediated picture and say that distance it creates between the evidence and the hypothesis makes this into a kind of higher order evidence. So it's not direct evidence about it. What it's telling us is that our evidence implies certain things, other evidence that we already have. So it's not distinct evidence at all. It's really evidence about our evidence. So why is that useful? Well, because climate modeling is so hard. These models are, they have this modular, coupled and distributed status. So they're made up of many subcomponents, which are often developed separately, and then they're assembled together. Now that's done for kind of practical reasons, but it makes life difficult because the systems are coupled. So you can have it's all very well to have a model of the ice and a model of the land and then put them together, but really the ice is on the land and they interact in important ways. Then you have to do a lot of work to couple the systems, ensure that the right feedbacks and interactions are there. And in fact, this work is done by a great many people at different times and places. If you count all the people who connected the data and all the people in all the modeling teams, we're talking hundreds of people. And so it's really not obvious what our evidence implies, nor is it obvious how we could make these inferences ourselves, where the inference involves these many hundreds of time steps that the simulation gives us. So the thought is that models reveal implications of the evidence that no individual could see otherwise. Okay. Now, I think this is kind of interesting. It's potentially a kind of philosopher's question. I'm not sure how much turns on whether it's first order evidence or higher order evidence, except perhaps for the thought that some might think that higher order evidence is in some sense less good than first order evidence. But I think that this kind of explanation of the fact that it's generating things which are new for us, given our inability to perform instant computations that are absurdly complicated, means that it's really valuable in any case. Okay, so let's talk a bit about uncertainty. I said the climate's really variable, and it's got this short-term variability in terms of like the weather changing day to day. We're not interested in that. Like, we're not trying to predict what the weather will be like on the 1st of June in 2200. We're trying to predict the climate state in the year 2200. But we do want to capture some long-term variability. So climate scientists have to distinguish the natural variability of the system from sources of uncertainty. And they face many of these. So they're uncertain about past and future forcings of the climate, where forcings is like, in this case, the stuff that we're doing, putting in greenhouse gases, aerosols, and so on. And that uncertainty is just because they don't know about the future political situation of the world and the future development of technology and so on. Secondly, they're uncertain about how the climate system will in fact respond to forcings. So that's a question of physics. This is an uncertainty about the nature of the system. And it has to do with the fact that we're pushing the climate outside of an observed historical region. And then they're uncertain about their models, uncertain about how well any of their climate models describe the climate system. And part of the reason for that uncertainty is because of the above points, that it's quite difficult to assess how well they're doing. Also just because of this sort of simple fact that the key thing we're interested in is these long-term future predictions of a system where the hypothesis is that we've pushed the generating process out of its historical range. And so it's a deeply difficult task. But it also is related to these things I said before, that mathematical models leave out, they simplify, they idealize, and that computer simulations in particular discretize, parameterize, and approximate. So how do they manage this? Well, it depends on what the variability and uncertainty is. So for climate variability, there the key is to just build physical understanding. You expect a certain amount of variability. And so that, in a sense, is the least worrying part. The uncertainty about forcings, well, the climate physicists just sort of shunt that off to one side, and they say, well, we're just not responsible for predicting the future of the kind of global economy and political agreements. So that's dealt with through the use of scenarios. And I'll talk a bit more about those. Response uncertainty, how the system itself will respond, is dealt with through a fairly standard procedure of sensitivity analysis, where you basically vary the different parameters and try to see what the impact would be. Model uncertainty is a more difficult one. And if you're just not sure how good your models are, it's very unclear how you can use them. And the tool that climate scientists have adopted is basically using collections of different models together. So I'll talk just briefly to close about these two with stars next to them, scenarios and collections of multiple models. So scenarios first. A major source of uncertainty for climate science is just human activity. What we'll do, whether we'll do what we've said we'll do, and so on. And in previous IPCC assessments, the way that this was dealt with is that the scientists just used these scenarios which specified levels of forcing. So they just specified a certain level, basically, of the emissivity of the atmosphere, which is the physics variable that corresponds to how much greenhouse gases we put into the atmosphere. But those were just, they were specified that way because that's what they care about for the models. They just wanted to know how much stuff was in the atmosphere because that's what informs the changes in its evolution. What they've switched to doing now is using these socioeconomic scenarios, which are kind of narratively defined storylines about how the development of human society will go over the next 100 years. And so there are 5 of them. They have these kind of names that are meant to be evocative. So the first one's called sustainability, then there's middle of the road, regional rivalry, inequality, fossil-fueled development. And each of them describes a plausible unfolding of how things will go in terms of trends in geopolitics, economic development, energy, obviously, but also global justice issues, as you can see. They then correspond to specifying these greenhouse gas emissions curves, which means that the climate physicists can use them to initiate the models. So each one of them is, it kind of begins with a story about what will happen in society and ends with just a curve, like here are a few curves. This is CO2 concentrations in the atmosphere over the next 100 years under a bunch of these different scenarios. So this is all the physicists care about. But what they are really is just a set of descriptions of possible things we might do. And so what that does is it means that climate physicists are producing what they call projections, which is a kind of conditional prediction. They're not claiming that this is a prediction of what will happen given the current state of the system. So this first quote says, climate change experiments with models do not depend on initial conditions, but on the history and projection of climate forcings. So it's just saying, assuming you guys do this, here's what we think will happen. So here, I won't read the other quotes. But what that means is that when we understand this evidence, we have to understand it as a kind of conditional claim about what will happen. And these scenarios themselves are not assigned likelihoods officially in any case. So the projections overall are not assigned any probabilities. Informally, people will say things like SSP5 is unlikely because it involves no mitigation efforts. But I mean, as far as the climate scientists who do the modeling is concerned, they're not taking that into account. And what that reflects is perhaps some kind of social science thinking, but more likely, I think, just kind of optimism that we will do some things. But the predictions themselves are just conditional. All right. I think I'm running a bit late, but I can do like maybe a couple minutes on this, multiple models. All right. So the other thing was that we don't know how good these models are for various deep reasons. We don't know how good they are at capturing the actual physical relationships. So what ends up happening is that collections of models are used. So there are lots of different global climate models. There are about 50 groups around the world who develop these complex models. Some of the differences between them are kind of structural differences in understandings of what the physics really is. They also have different parameterization schemes, different ways of dealing with clouds, different ways of handling the process of converting it into a computer program. But they have a lot of overlap. They share code. They all went to grad school together. They share a lot of techniques, as you would perhaps expect. And they use collections of these models to do what they call intercomparison studies, where they study the distribution of results that you get from a whole collection of models. And these ensembles of models represent some of the uncertainty that we have, which we collectively have, which informs the fact that there are all these different models. And they're thought to provide a tool which can help us to find the best answer despite this disagreement and uncertainty. So they're quite different. Here's a chart showing you global mean temperature projections, and each of the thin blue lines is a model. And so as you kind of go forward in time, they end up disagreeing to a fair degree. I mean, qualitatively, this is the good thing. They all show increases. Even in the best case, they show significant increases that we should pay attention to. But nevertheless, the spread can be quite large. And maybe more importantly, they disagree in ways that mean that their errors are quite different. So this kind of heat map shows each of these lines, each row is a test variable in a historical experiment. So where they were just asked to reproduce past climate data. Each column is a model, and the direction, the color is a kind of error in one direction or the other. All you need to see is that there are some that are biased in one direction, all blue, some that are biased in another direction, a bunch that are mixed. It depends on which variable you're looking at. The differences are significant and complex to understand. And so they do these studies for variable after variable, and it can be really hard to trace why they're getting the differences that they are. But nevertheless, the plan is to somehow use the collection together, like in this picture, to do better than you could do with any particular model. Okay, so one kind of question people are interested in is whether they can quantify the uncertainty that's in these collections of models. And traditionally, this is done by using probabilities, the kind of core tool of statistics. And importantly, probabilities have a kind of well-defined role in decision-making. And traditionally, what climate scientists did is that they just took these model results, basically treated them like data points and did normal statistics on them to generate probabilities. And now there's quite a large discussion about how reliable that process is and whether different ways of understanding uncertainty should instead be used. So I think I'm going to skip over this one. The issue that we're interested in is that we're not sure whether these models are the right models. And climate scientists are trying to make use of the fact that they have many of them to investigate that uncertainty, whether or not they're the right models. But the collection of models we have is just what they call an ensemble of opportunity. It's just a collection we happen to have built for historical and geopolitical reasons. Like, it's important for countries to have their own climate modeling team. And so we get another model. So the collection's assembled from the ones that we happen to have. It wasn't designed in any sense to span the uncertainty that we in fact have as a group of scientists about these important questions of like what the right physics is or how to parameterize clouds. So can we nevertheless use this collection we happen to have to resolve this uncertainty in the science? And it kind of seems intuitively like when they agree on something, that must signal to us that we're better on that variable than on other variables. But it's unclear how exactly to support that inference. So we skip this one. So one of the things I said that people have done is to kind of treat the distribution of model results as an indicator of probability, to do statistics on them in the same way as you would treat frequencies in observational data to construct a statistical model. But I think there's a really important kind of challenge to this way of thinking. It seems to imply that either the collection of models we have is somehow a sample of models, or that the model results that we have, these predictions about temperature, is something like a measurement of potential climate states. But the ensemble that we have is just an opportunistic collection. And it's very unclear, if you think this way, what the kind of population that you think you're sampling even is. These simulation models are kind of representations of the physics. It's not clear what it would mean to have a population of all simulation models. And it's not clear that some of the basic statistical reasoning that we use would apply in this case, that the mean of the population would in some sense be the true model, or that the mean of all results you could get from all models would be the true result. And so it's really difficult actually to understand whether these standard statistical procedures work in the way that we're used to. Let me skip this, I'm running out of time. So yeah, here's a final thought. One thing that people have proposed instead is to just retreat to regarding climate models as providing us with possibilities. So they specify states of the climate that are possible in the sense of consistent with relevant background knowledge. And this fits with that kind of higher order picture of the evidence we get from models that I referenced earlier. And there are two issues with this way of thinking. So one is we shouldn't confuse possibilities that we happen to have identified because we've calculated them with everything that is in fact possible. What we've done is run a certain number of experiments on a certain number of models. And so it's good to know that this range of states of the future climate is possible, but it's not the case that those are the only possibilities, that we've spanned the full space of uncertainty. It's also not clear how to make decisions when you just get told that something's possible. So it requires altering some of the ways that policymakers and others think about making decisions. Probabilities have a well-defined decision theory, whether it's expected utility or various tools in risk assessment. But if you just have possibilities, you have to adopt different strategies. But they do seem to fit into some decision theories for radical uncertainty. So you can make cautious decisions where you take all possibilities seriously and choose the actions which do well in the worst possible states. You can do robust decision-making, where you take them all seriously and choose actions that do well across a range. Or you can even attempt to construct a mathematical theory, as people have done in possibilistic theory, which attempts to reproduce some of the numerical features of probabilistic theory, but in a way that makes fewer assumptions. And there are also decision theories for those. But what that requires essentially is reorienting a lot of the thinking that people do with probabilities, and rather than attempting to distinguish between any of these states and say which one's the most likely, we instead say, we know these ones are possible. Some others might be possible too, and we'll try to quantify that instead. But that makes life much more difficult for people who are trying to use these climate models. Okay, so that's it. Climate science is really hard. There are a lot of strategies to manage the uncertainty, and the evidence that it generates is often indirect, higher order, and mediated.